All right, so in this section here, we're just going to take a look at taking the factoring, solving for x-intercepts, solving for the vertex material that we've done, and we're going to put it all together into just solving some problems when we are doing some of the factoring and just kind of applying it to some real-world models. So to start with, just some review. Again, factoring. When we want to factor a quadratic, we first look for a common factor between our three terms. Here, if we look, our common factor 4, 10, and 24, there is one. And that common factor is going to be 2. And when we factor that, we get 2x squared minus 5x minus 12. So there we've factored out our common factor. And now we want to factor this trinomial. And again, you can continue that down right here. But I know for some, it's convenient to do it separately. So I'm going to just pop over here. We have 2x squared minus 5x minus 12. So I'm just borrowing that from right here. We're going to factor that, and then we will then pop that back in once it's factored. Starting off, we're using that decomposition method. So multiplying the 2 and the negative 12 to get negative 24. We're looking for two numbers that multiply to 24. Negative 24 add to negative 5. Looking at numbers that are going to multiply to 24, 5, and add to negative 5. We'll probably look at 8 and 3, negative 8 and positive 3. So negative 8 and positive 3 are going to be a pair of numbers that would satisfy that requirement. So we're going to rewrite the middle term here, the negative 5, with those numbers. So we have 2x squared minus 8x plus 3x minus 12. So I've rewritten those numbers, and now I'm going to do my factor by grouping on each of the pairs. So I take that first pair, factor out the 2x in that case, and I'm left with x minus 4. In the next pair, bringing down the sign of the next term, common factor is 3, and I'm left again with x minus 4. Those two brackets are the same. That means we're on the right track here in most cases, and we will common factor that out. X minus 4, 2x plus 3. And there it's factored. If you put these in the opposite order, positive 3 and negative 8, then everything here would just be flipped around in the opposite order, but you'd end up with the same brackets. And then we will take that and transfer this over to here to replace what's here. So 2x minus 4, 2x plus 3. And there we've factored that down. So there is our full factor right there. Now that we've factored that, we can use it to find some information, such as the x-intercepts, and then once we know the x-intercepts, we can find the vertex. When we're finding the x-intercepts, our only focus is on these brackets portions. We're going to set each of those equal to 0. So we'll come down here, when we're solving that for x-intercepts, the y value is 0. So it's technically y equals 2x minus 4, 2x plus 3. And again, that's just because the y value at the zeros, when it crosses the x-axis, the x-intercept is 0. So we set each of these brackets equal to 0 because that's what's going to make this happen. So that's equal to 0, or 2x plus 3 equals 0. One of those two cases is what we're going to get. If we solve this one here, then we have x, and then we move that negative 4 over. We're going to have 0 plus 4, or just 4. On this side here, we move the 3 over. We got 2x equals 0 plus 3. Or sorry, 0 minus 3, rather. And that would be 2x equals negative 3. And then we divide by the 2 to get the final answer of negative 3 over 2. Again, I like fractions, especially halves, quarters, eighths, and things like that, as I mentioned before, but you could also write that as negative 1.5. Both are correct. So now we know the zeros of the equation there. That is where it's going to cross the x-axis. And finally, when we were finding the vertex, we found the x value of the vertex by taking those two zeros, adding them, 4 plus, and here it's probably easier to use the decimal. So we add those together and divide them by 2. That's going to find the middle of those two values. And once we have the middle of those two values, we can find the zeros. We can find the vertex. Because that'll put us right in the middle of the zeros where the vertex is. So 4 plus negative 1.5, that's 4 minus 1.5, or it's going to be 2.5 divided by 2. And when we divide 2.5 by 2, we're going to get 1.25. So there's our vertex x value. So now we have to find the y value of the vertex. So this is the vertex x value. That's our axis of symmetry in the middle. Where's our y value? All we got to do is go back up, take our equation, and sub that in. And so we'll sub that x value into the equation. Y equals 4 times 1.25 squared minus 10 times 1.25 minus 24. So just plug the x value into the original equation, and I work that out. And again, this is a chance to pull out your calculator if you want, especially working with those decimals and squaring them. And I got negative 30.25. So there we now have the x value and the y value of the vertex. So the vertex is at 1.25 and negative 30.25. So now that we have these pieces of information, we can use those then to plot a graph, sketch it out, recognize those key values. Again, the vertex and the intercepts are going to be your key values there. So now we'll take a look at a couple examples of what we can do with this in terms of some mathematical models. So the first one here, we got a bridge over a river is built in the shape of a parabola. The equation h at d equals negative 0.005 times x plus 50 times x minus 50. So that models the height of the bridge in meters versus the distance in meters from the middle of the bridge. So we're measuring distance based on the middle of the bridge in this case. And we want to find out how wide and tall the bridge is. So here I've already factored this. I've left this in factored form. So we don't have to factor it. We just have to now find our x-intercepts and then find the vertex. We find the x-intercepts because if our bridge is a parabola, then that means our x-intercepts, the distance between them, will give us the how wide the bridge is, and then the height will be the vertex peak. So let's calculate that now. And so we'll start with our x-intercepts. So finding our x-intercepts, we have the height 0. And then 0.005. And again, this is just good mathematical form. I know some of you might skip this step and of setting equal to 0, but it is good form to recognize. So we're finding the height of 0. That means one of these two guys has to be 0. So either x plus 50 equals 0 or x minus 50 equals 0. And in that case, we're going to get x equals negative 50 when we work that first one out, and x equals positive 50. So those are my x-intercepts. So if we look at my little sketch here, I got an x-intercept at -50 and an x-intercept at +50. How wide's the bridge? Well, what's the distance from -50 to +50? And to find the distance between 2 points, we just subtract them. So we have the width equal to 50 minus the -50, and that's going to give us 100 meters. So our width of the bridge here is 100 meters, but then we need to also find the height of the bridge. So that's going to be from the y value of our vertex. So if we want to find our vertex, then we need to take our zeros and add them up to get the x value, the middle axis of symmetry, so -50 plus 50 divided by 2. That's just going to be 0 divided by 2, or 0. So our x value is 0. We then take the 0, plug it into the equation to get our respective y value. So the height at a distance of 0 meters from the middle equals -0.005 times 0 plus 50 times 0 minus 50. And again, if you feel like, you can plug the calculator. 0.005, and we work that out to a good old 12.5. Sorry, positive 12.5. Which makes more sense in this case. So we got a 12.5 as our height. So that height up here, it means this bridge here from here to here is 12.5 meters. So there's our height. And then you could make some sort of statement to that effect. The width is 10 or 100 and the height is 12.5 meters. So we can use this to find some information given the model of it. Could be useful in construction, could be useful in taking this bridge and then putting it into a virtual computer simulation, some sort of architectural program that would then allow the computer to make an accurate model of that bridge. And then we could do any modifications, do things like stress testing and all that kind of stuff with it using the proper mathematical notations. Better to do stress testing on a computer first than to actually build the bridge and have people walk across it and maybe it collapse on them or something. Now, the next example here that I got for you is has to do with radio telescopes. So radio telescopes are just generally big parabolas. In circle form, they're like a satellite dish is what you'd probably call them in a lot of cases, but they work in the same principle as the radio waves come from space and hit them. They reflect, and the nice thing about these types of shapes is they reflect back to a point on there. So you'll notice on most satellite dishes that there's that little piece in the center sticking up. That's where everything actually reflects into. And then that's where it collects all the data. So these large radio telescopes work in the same principle. They get pretty big. Some of them oftentimes buried in the ground because they're so large. To make structures to support them is very difficult. But here we have a new radio telescope that has a dish modeled by the equation y equals 0.0028 x squared minus 0.672 x, where y is the depth of the dish and x is the horizontal distance across, both of these being in feet. We want to know how wide the dish is and what the depth is at the lowest point. Now this one here looks a little scary. We got all these decimals in here and we haven't really worked with dealing with all these decimals. So what do? As we move into, as you start modeling things in realistic situations, you're going to have these decimals cropping up. Not everything's going to be nice even numbers, but it's actually really quite easy to work with. When you have a situation like this, we just common factor that out. So the first thing we're going to do is factor the equation as best we can. So we got y equals 0.0028 x squared minus 0.672x. So whenever you come into a situation like this and you got these crazy decimals, factor this out. Let's get rid of this decimal right here. So we're going to make that our common factor. 0.0028, and then they both have a common factor of x as well. So I'm just going to factor that right out. In this case here, this is just common factoring because it's not a trinomial, making it easier on us. So we got 0.0028x, and then what's left when we divide these by 0.0028x? Well, 0.0028 divided by 0.0028 is just 1. X squared divided by x just leaves us with an x inside here. In the next part, it's going to be negative, as we're dividing positive by negative. And if we take 0.672 and divide that by 0.0028, we get 240. And the x's will factor out. So there, that looks a little bit nicer to work with. We can get our zeros now from that. That's completely factored. And again, not a trinomial in this case, so we just common factored out the 0.0028x. And again, we just picked that number because that was the a value. Use that when you have these crazy decimals, and a lot of times it'll work out nice like this. What do we do next? Well, we want to find our x-intercepts next. So we find our x-intercepts. We set this equal to 0. Y equals 0.0028x, x minus 240. Same rules, again, with a single x like this, it's treated, remember, x is the same as a bracket with x minus 0 in it. Those are exactly the same thing, so we can, just note that's not, accidentally skipped over that part of what I said. That's not part of the question, just to note. So this x here, we can just set it equal to 0. We just got one of the zeros right away, x equals 0. Or we got x minus 240 equals 0. And if we solve that one, we move the 240 over. It becomes 0 plus 240, or just 240. There we have our zeros. So this is nice. So now, we're going to have this parabola, and it's positive, so it's opening downwards like this. We got a 0 right there, and then this point over here is 240. So how wide is the parabola? Nice and easy. This parabola is 240 feet wide from this case. And then the height is going to be given by, again, our vertex. So with our vertex here, we find the middle of our x values. So 0 plus 240 divided by 2, which is going to give us 120. Substitute that into the original equation. Y equals 0.0028 times 120 squared minus 0.672 times 120. And again, probably convenient just to plug that into your calculation device. And it works out to a negative 40.32. So what that means is that from the ground level here, this is probably one of those satellites that's buried in the ground, as I mentioned earlier. This depth here is 40.32. So it's 40.32 meters deep at its lowest point. So, we do our therefore. I'll do it this time. So the width is 240 feet, and the depth is 40.32 feet at the lowest. And you might ask, why didn't you put the negative sign there? Quite simple. We want to know the depth. So if we were graphing this, if we put this parabola on a graph, I'll do it just over here. It's going to look like this on the graph, with this being ground level here. But if you were giving the depth, you would just say that's how deep it is. It's about 40 feet deep. You wouldn't say that it's negative 40 feet deep. So we just don't need the negative sign there in terms of mathematically it's there, but in terms of the real situation, it's not required. So there's some examples. Again, when you're working with the case of some of these crazy decimals, use that when you're factoring as your common factor and factor that out, and then it will leave you in many cases, and the ones we're going to work with anyways, with nice pretty whole numbers that are easy to factor, find zeros and whatnot. And that one is it.